Hello everyone. Today we are going to talk about high-resolution image synthesis with latent diffusion models, motivation, and related works. The field of image synthesis has seen significant advancements, with diffusion models showing impressive results in image synthesis and beyond. However, these models are computationally demanding, requiring extensive resources for training and evaluation. The current state of the art in class-conditional image synthesis and super-resolution is defined by diffusion models. However, these models are often confined to data with limited variability due to their adversarial learning procedure. Existing methods, such as GANs and autoregressive transformers, have their limitations. GANs often exhibit mode collapse and training instabilities, while autoregressive models require billions of parameters to model complex distributions of natural images. The computational demands of diffusion models pose a challenge to the research community and users in general. Training such models requires massive computational resources, and evaluating an already trained model is also expensive in time and memory. Limitations of existing approaches. Existing approaches often require task-specific architectures, limiting their versatility and applicability across a wide range of tasks. The adversarial learning procedure of GANs does not easily scale to modeling complex, multimodal distributions. Autoregressive models, while capable of modeling highly complex distributions, involve billions of parameters, making them computationally expensive. Existing diffusion models are computationally demanding, requiring repeated function evaluations and gradient computations in the high-dimensional space of RGB images. This leads to superfluous computations and unnecessarily expensive optimization and inference. Reasons for new approach. To increase the accessibility of powerful diffusion models and reduce their significant resource consumption, a method is needed that reduces the computational complexity for both training and sampling. The goal is to reduce the computational demands of diffusion models without impairing their performance, thereby enhancing their accessibility. The paper proposes to separate training into two distinct phases. First, training an autoencoder to provide a lower-dimensional representational space, and then training diffusion models in this learned latent space. This approach aims to provide more faithful and detailed reconstructions than previous work, and can be efficiently applied to high-resolution synthesis of megapixel images. Problem settings with existing methods. The authors are addressing the issue of efficiency in training and sampling of denoising diffusion models. This problem is significant as it impacts the quality and versatility of models used in the field of conditional image synthesis. Previously, these models may not have been as efficient, requiring task-specific architectures and potentially degrading in quality over time. Importance of the problem. The efficiency of training and sampling in denoising diffusion models is crucial for their performance in conditional image synthesis tasks. Improving this efficiency can lead to better quality models that do not degrade over time and do not require task-specific architectures. This can open up new possibilities for the application of these models in various tasks. Previous solutions and their limitations. Previous solutions have attempted to improve the efficiency of these models, but they often required task-specific architectures, limiting their versatility. Additionally, these methods may not have been as efficient, leading to a degradation in the quality of the models over time. New key improvements. The authors propose latent diffusion models as a solution to these problems. These models are designed to improve efficiency without degrading the quality of the models. A cross-attention conditioning mechanism is used to further enhance the performance of these models. The models are trained on the COCO and OpenImages datasets, and their performance is evaluated using quantitative evaluation and additional samples. The learning rates of the models are maximized for stable training, leading to improved efficiency in both training and sampling. These improvements allow the proposed models to surpass the performance of state-of-the-art models without requiring task-specific architectures. Section 1. formulation of the problem and approach, the authors of this paper have identified a need for improved efficiency in the training and sampling of denoising diffusion models. They have approached this problem by proposing the use of latent diffusion models, which are designed to enhance both the training and sampling efficiency without compromising the quality of the models. This approach is a departure from previous methods that may have required task-specific architectures and could have resulted in a degradation of model quality. Section 2. Experimental design and methods. The authors have designed a series of experiments to test the effectiveness of their proposed latent diffusion models. These experiments involve training the models on two datasets, COCO and OpenImages, and then evaluating their performance using quantitative evaluation and additional samples. The authors have also incorporated a cross-attention conditioning mechanism into their models, which is a novel method that has not been used in their previous approaches. Section 3. Improvements and innovations. The authors have made significant improvements in the efficiency of denoising diffusion models through their proposed methods. Their latent diffusion models have demonstrated favorable results when compared to state-of-the-art methods, even surpassing the performance of these methods in some cases. Furthermore, they have managed to achieve these results without the need for task-specific architectures, which is a significant innovation in this field. The authors have also maximized the learning rates of their models for stable training, which is another key improvement over previous methods. Technical results. 1. The proposed latent diffusion models have shown significant improvements in efficiency. They have been trained on the COCO and OpenImages datasets, demonstrating favorable results compared to state-of-the-art methods. 2. The COCO model matches the performance of recent state-of-the-art models in layout-to-image synthesis. When fine-tuned from the OpenImages model, it surpasses these works. The OpenImages model outperforms the results of Jan et al. By nearly 11 in terms of FID. 3. On Celeba HQ, a new state-of-the-art FID of 5.11 was reported, outperforming previous likelihood-based models as well as GANs. The models also outperform LSGM, where a latent diffusion model is trained jointly with the first stage. 4. The models outperform prior diffusion-based approaches on all but the LSUN bedrooms dataset, where the score is close to Admiral, despite utilizing half its parameters and requiring 4 times less train resources. Key results and implications. 1. The results imply that latent diffusion models can significantly improve the efficiency of denoising diffusion models without degrading their quality. 2. The cross-attention conditioning mechanism can be used effectively in a wide range of conditional image synthesis tasks without task-specific architectures. 3. The models can surpass the performance of state-of-the-art models, indicating the potential of the proposed method in improving the efficiency of denoising diffusion models. 4. The learning rates of the models can be maximized for stable training, suggesting that the proposed method can be used to improve the stability of training in denoising diffusion models. Ablation studies and implications. 1. The paper also presents an ablation study where the models were trained on different datasets and evaluated using different metrics. The results of these studies further confirm the effectiveness of the proposed method. 2. The ablation studies show that the proposed models consistently improve upon GAN-based methods in precision and recall, thus confirming the advantages of their mode-covering likelihood-based training objective over adversarial approaches. 3. The results of the ablation studies imply that the proposed method can be effectively used in a wide range of applications, including text-to-image image modeling, semantic synthesis, super-resolution, and inpainting. Key highlights of the paper. 1. Key insights. The paper provides significant insights into the potential of latent diffusion models in improving the efficiency of denoising diffusion models. It also highlights the effectiveness of a cross-attention conditioning mechanism in conditional image synthesis tasks. 2. Key contribution. The paper's primary contribution is the introduction of latent diffusion models that improve both the training and sampling efficiency of denoising diffusion models without degrading their quality. The models are trained on the COCO and OpenImages datasets, demonstrating their versatility. 3. Key idea. The central idea of the paper is to leverage latent diffusion models and a cross-attention conditioning mechanism to enhance the efficiency and quality of conditional image synthesis. The models are trained in a fixed space, avoiding the difficulty of weighing reconstruction quality against learning the prior over the latent space. 4. Key results. The proposed models demonstrated favorable results compared to state-of-the-art methods. The COCO model matched the performance of recent state-of-the-art models, while the OpenImages model surpassed the results of Jan et al. By nearly 11 in terms of FID. The models also showed improved efficiency in both training and sampling. 5. Key conclusion. The paper concludes that latent diffusion models can significantly improve the efficiency of denoising diffusion models without degrading their quality. The cross-attention conditioning mechanism can be used effectively in conditional image synthesis tasks, and the proposed models can surpass the performance of state-of-the-art models without task-specific architectures. The learning rates of the models can be maximized for stable training.